Let's talk about sampling. We're starting in Chapter 8. This is in Section 8.1 of the text on sampling. This is the first step in the conversion of a continuous time signal to discrete time. First we'll talk about ideal sampling. Understanding ideal sampling will help with understanding practical sampling. So here we're going to multiply x of t by our impulse train to come up with a sampled version of x of t. We'll call that sampled version x, and I'll put an overbar over it. And so, for example, just some pictures here. X of t may be some function like this, function of time. This is our continuous time function. Our impulse train, and assume that all of our impulses are equally spaced. They're spaced with t apart, capital T. And they all have the same weight. So this is our delta capital T of t function, and it extends to minus infinity to the left and plus infinity to the right, delta T of t. So from the multiplication property of the impulse, what I'll get out when I multiply these together is just another train of impulses whose weights are now equal to the corresponding values of x of t, x of t evaluated at the sample instances. And so I'll just kind of sketch in what x of t looks like here as a dashed line, but the result of this multiplication is actually still an impulse train, but now I'll show the impulses with different heights corresponding to the different weights obtained by multiplying the impulse and x of t. So we want to get some idea of what's going on here when we sample a spectrum. We want to talk about what the spectrum of this sampled signal looks like, x over bar of t, and in order to start that, recall that we can represent our impulse train as just an infinite sum of shifted impulses. And then recall that from the multiplication property of the impulse, that if I multiply x of t by delta t minus t0, the result is an impulse whose weight is now the function evaluated at t0. And so I can write x of t as using this summation notation for delta t of t. I can write x of t as x over bar of t as x of t times this infinite sum of impulses, delta t minus nt. Each of these impulses is located at n times t. So applying the multiplication property, infinite sum from minus infinity to infinity of x of nt delta of t minus nt. And that's this representation we have here for this this train of impulses. I guess note at this point this is all theoretical. We can't actually generate x over bar of t, we can't practically generate a single impulse, let alone an infinite train of them. But again, understanding what's going on here with ideal sampling will help us to understand practical sampling better. Also note that x over bar of t, although it's not a practical signal, it is a continuous time signal. A very strange one, but it is still a continuous time signal. Let's take a look now at the Fourier transform of x of t. We'll call that x of omega. And since I can write x over bar of t as the product of x of t and that impulse train, I can find out the spectrum of x over bar of t by convolving x of omega with the Fourier transform of my ideal impulse train. And if you recall, talked about this in a previous lecture, Fourier transform of an impulse train is an impulse train in the frequency domain. So where all of the impulses are separated by, I'll use the notation omega s, where omega s is equal to 2 pi over t. Corresponding frequency in hertz is then just 1 over t, the reciprocal of our sampling interval. And now, since x of omega involved with an impulse located at minus omega in convolution with an impulse is trivial, it just shifts the location of the function. I can carry out the convolution of x of omega with this infinite sum to get an expression for the Fourier transform of x of my ideally sampled signal. So that's going to be equal to 1 over 2 pi cancels out the 2 pi here. Have this sum, k equal minus infinity to infinity of now x omega minus k omega s. In order to get an idea of what this spectrum might look like, we're going to first consider the case where x of t is band limited. So we'll assume that x of t is band limited to frequencies less than what I'll call capital B hertz. Okay. Which, for example, a representative spectrum of x of omega, let's just say, looks like this. The shape's quite arbitrary, but it's limited to frequencies between 0 and capital B. Okay. And then now, referring back to my x over bar of omega, it's an infinite sum of shifted versions of x of omega. That's actually k times omega s. K going from minus infinity to infinity. So as long as the spectrum here of x of omega is narrow enough, and we'll talk more about that in just a second, then what x over bar of omega will look like is again just a sum of shifted versions of x of omega. With k equal to 0, I have x of omega. With k equal to 1, This will be now shifted to omega s. This width is now 2 times b. So this lower frequency is omega s minus b. The upper frequency is omega s plus b. And then also at minus omega s corresponding to k equal minus 1. This would continue at 2 omega s minus 2 omega s at 3 omega s, 4 omega s, on and on and on forever. So this Fourier transform of this ideally sampled signal is actually has infinite bandwidth. Okay, and going from and the Fourier transform consists of replicas of the spectrum of x of t, but now repeated in frequency every omega s radians per second in corresponding frequency in hertz. This would be, we call these frequencies fs, 2fs, and so on and so forth. Actually, I was going to use the bandwidth actually and call this, well, it's fine, I'll leave b in radians. I thought I'd call it 2b, but we can see here from the condition that as long as these replica don't overlap, so as long as omega s is greater than 2 times b, where b is actually in radians per second, then there's no overlap between these replica. That means I've got some space here between the two. So this is equivalent to f of s being greater than 2 times b over 2 pi. Let me call this b over 2 pi equal to a lowercase b, where b is in hertz. So this is equivalent to f of s greater than 2 times b, and this lowercase b is the maximum frequency in x of t. Or equivalently, this would be, since f of s is equal to 1 over t, 1 over t has got to be greater than 2 lowercase b, or the reciprocal of this, the sampling time, has to be less than 1 over 2b, where b is the max frequency in x of t. So as long as this condition is met and we've got space between the replica, then I can recover x of t, the original continuous time signal, from its ideally sampled version with a low pass filter that has this frequency response. It's just equal to 1 between minus b and b. This is in hertz, or for omega we call this minus b and plus b, and so this is the frequency response of this low pass filter. Then recall that I can recover x of t either by convolving the ideally sampled version with the impulse response of this filter, or in the frequency domain, the equivalent operation is multiplying the spectra of x over bar of omega by the frequency response of the filter. So what this low pass filter does is it passes through the the replica that's centered at omega equal to 0 and filters out all of the other high frequency replica. But by doing that, I've recovered a spectrum that's identical to that of my original signal. So I've been able to recover my original signal. So what we've discovered here is that as long as I sample at a rate Fs greater than 2 times the highest frequency in my signal. So for example, if I'm working with a signal, the highest frequency is 10,000 hertz. If I sample that, ideally sample that signal at a frequency greater than 20,000 hertz, 2 times 10,000, then I'm going to have space between these replica in the sampled signal, and I'll be able to recover then the original spectrum and the original signal from that sampled signal. This is known as 2B is known as the Nyquist rate. So I need to sample at greater than the Nyquist rate in order to recover my original signal. And if we sample below the Nyquist rate, we're going to recover a distorted version of x of t.